Well, I think we can start. Welcome back, everyone. So today's class, we are getting over the hump. I think chapter 15 is, like we mentioned quite a bit in the notes on Monday, probably the trickiest chapter in the entire course, but we're getting through it. The major trickiness is we have a two-way table of outcomes that can occur whenever we run a hypothesis test. We could make a type 1 error. That's in probability alpha, the significance level of the whole test. Or we can make a type 2 error in probability beta. We're not going to directly compute beta. What we'll be computing is power, which means we've indirectly computed beta the moment we've computed the power of a test. But what also makes all this really quite tricky is there's a lot of language that goes along with it. We have to put together the significance level alpha. If our p-value is less than alpha, we reject the null hypothesis in favor of the alternative. But we can only calculate the power of the test if we also are mindful of what is the effect size, the smallest quantity that has practical significance in the population. Say, for example, if we're just measuring the heights of individuals, and our tape measure gives us measurements to the nearest 1/8 of an inch, that'd be a natural effect size. We can only measure to 1/8 of an inch. And so we want to devise a test that can detect a difference within 1/8 and reject it with a high probability. That's what power is when it comes to the test. Then putting that all together, we have to also note there are only two conclusions to a hypothesis test. We'll either say we found significant evidence that the alternative is true, or we'll say we failed to find that significant evidence. So a lot of concepts that it's all brought together when we think about power. So we're going to today calculate the power of a test in chapter 15 for a left tail test. I believe the homework exercise involves a right tail test. And I put the two tail test here just for the curious. Here's how the syntax would go if you want to take a look. Well, we're going to refresh what we did before we delve too much further into the last example 4 on chapter 15. Any questions at all to start us out today, folks? Okay, so let's take a look where we left off. It's honestly kind of hard on the eyes because there's a lot of things we said. So let's do this in stages. Let's kind of hide some of that stuff. We were doing a test to detect sulfur dioxide, responsible for acid rain. Excuse me, let me say that better. We're worried about sulfur dioxide, but we are testing the pH of rainfall. And these are measurements made on different days in a Canadian forest. We're told that these measurements follow a normal distribution. And if we find that the pH is less than 5, indicating high acidity, we'll say that that was caused by emissions of sulfur dioxide set off by industry in Canada. So this is a very high stakes test. It could have been a government body that commissioned this test to be done. The conclusion of this test can have huge ramifications. And so before they even calculated any data whatsoever, took any sample, they would carefully set up what they're going to test. The significance level alpha was carefully chosen. They went for a 5% significance level. That tells us they're willing to accept a type 1 error at a 5% chance. Do the study 20 times, and one of them is going to make that type 1 error. That's kind of a bold decision for something that's high stakes, but they went for it. The other big thing that they said in this problem is assume differences smaller than a pH of 0.3 are not considered to have practical significance. That's a bold statement as well, but what's going on there is meteorologists, environmental scientists probably all got together to come up with that value, and they were telling us that that's the effect size. That's going to be the value that's as large as possible, 0.3, but still quite small, for which if we can detect something to that degree, we will say we'll have a high power of a test if it's able to make that detection. Difference of as large as 0.3. So putting that all together, once we found the effect size, we have a specific alternative hypothesis that goes along with it. So we are testing next the null against the alternative, but if we're going to compute power, as we will in these notes, Let me scroll down just a little bit more. Let's try and show this in stages. We have to say exactly what the specific alternative is. So we go from the fact that it's a left tail test. The hypothesized value, mu naught, is 5. It has to be 5 here as well. If the effect size is a 0.3, then we subtract 0.3 from this 5. If it's a right tail test, I think it is a right tailed in the actual homework exercise, then whatever this value is, you would add for your specific alternative. So here we subtracted, we have a specific alternative of 4.7, and that's going to allow us to calculate power and the probability of a type 2 error indirectly as well. Okay, that's the refresher on the problems so far. Any questions or comments at the moment? Okay, again, before any data is collected, there's a lot of work that goes into this. They are going to decide on the effect size, the type of the test, the alpha level, the level of significance, the benchmark they have to reach before they even reject the null hypothesis. But they would also absolutely do this. They're going to put into words, so everyone knows the ramifications of both these errors. What is a type 1 error, and words using the context and saying what the parameter is in context, and saying for the type 2 error. If we can't do that, we're being very blunt and incareful with our statistics. And whatever conclusions we make, we might be torn apart by industry if they don't like the changes that might come down the line if we say reject the null in favor of the alternative. So here's how we wrote out those errors. We first specified what the parameter is. Mu is the true mean pH of rainfall in a Canadian forest. We had to specify the specific alternative. We'll have to do the same kind of work. It's a homework exercise as well as an exam 2 question. And then we use these notes that we wrote down really carefully. Let me scroll to just this level. I'm going to put these notes, like I mentioned before, on the last page of our actual exam 2, just as a helper on writing out type 1, type 2 error. Well, type 1 error says the study found significant statistical evidence that the true mean pH of rainfall in the Canadian forest is less than 5, when in fact the true mean is a pH of 5 altogether. Let's take a close look on what is the logic in making that statement. In a type 1 error, we're right here in the body of the table, which means we have rejected the null hypothesis, which means we've concluded the alternative hypothesis is in fact true. We must have got a small p-value. So we've rejected the null hypothesis. We found significant statistical evidence that the alternative up above here is in fact true. The mean is less than 5, but that's not the reality of the population. We made that decision when in fact the null hypothesis was the actual reality. So we say here, when in fact the true mean is actually a pH of 5. The 5 was what we had here in our null hypothesis, and that's what we wrote out here. Then when we went to write out the type 2 error, we're in this case failed to reject the null hypothesis. That means instead of finding significant statistical evidence, we failed to find significant statistical evidence that the true mean pH of rainfall is less than 5, when in fact you have to say a specific alternative is true, and that is this value. We failed to conclude that the true mean is less than 5, when in fact it really is. It's exactly the assumption of 4.7 in pH. So again, the alpha, the betas here, they're written in terms of probabilities, but they're great guidance on what is type 1 error saying, what is type 2 error saying at the same time. We didn't interpret power, but we'll do that on the notes just for practice. And I think there's a homework question on interpreting power, so that'll be a good one for us to do as well. So there's, again, a lot of analysis, just pure context thinking that goes along with this, navigating a two-way table, dealing with conditional probabilities, where the conditional is if a specific alternative is true, or if a null hypothesis is true. Any questions at all, folks? Getting through that kind of a wall of text there. I'm going to park that cheat sheet just above so it's less of a distraction when we scroll through the problem. Okay, well, we skipped across part B, this question here, because it takes a bit of time to actually write this down on paper. This kind of a question, if it comes up either as a homework exercise or exam exercise, it's a subjective question. That means I can't take off points based on what your opinion, and that would be completely illogical. But for it being a subjective in your opinion kind of question, you do have to logically explain your choice. So that part is where the credit is going to be assigned. So some people, in their opinion, type 1 error might be worse. For some people, type 2 error might be worse. But it also depends on who are we talking about. If we're talking about just the average Canadian, they might be concerned about sulfur dioxide being released, causing more and more acid rain, devastation to their environment, those kinds of things. That might be really big issues to the average Canadian. But if we're talking more about specifically industry in Canada, if it's just those folks, and we're not too worried about the average Canadian citizen, one of these is definitely worse than the other. Now let's think about what happens in, say, a type 1 error to work through this. In a type 1 error, we've in fact rejected the null hypothesis when it was actually true. But if we reject the null hypothesis, read out the statement in blue, the study found significant statistical evidence that the true mean pH of rainfall in Canada is less than 5, so highly acidic rain. That might cause a lot of laws to be changed in Canada, which are going to reduce emissions of sulfur dioxide, which is going to be essentially a big tax on industry, scaling back the amount of revenue profits they generate. So this sounds pretty egregious, a type 1 error. What about a type 2 error? This could be worse. Let's think about this one as well. What happens in a type 2 error? Again, we're only thinking about industry and nobody else in this question. In a type 2 error, the study failed to find significant statistical evidence that the true mean pH of rainfall is less than 5. In other words, we failed to reject the null. We found no evidence of this alternative being true, when in fact, it is true. It's at 4.7. That's the assumption in the type 2 error. But would industry care about that? Probably not. I mean, that might concern them. Some of the big CEOs might lose sleep at night. Probably not, but some of them might. However, nothing's going to happen. If we fail to find evidence of this alternative, probably no legal changes are going to occur. The study is going to essentially say no evidence of this, and industry just keeps on doing as what they did before. In fact, they might scale up sulfur dioxide emissions because they just got away with it. So why not get more profit in the next quarter? So type 2 error is no big deal to industry. Type 1 error is a really big deal. And it's kind of unfair. This actually hurts all Canadians, really. We were going to say that we found evidence that this is true when it's not. Industry didn't do anything wrong. We're at 5. That's the pH of black coffee. It still doesn't sound great, but it's not as bad as this picture was. So to address a question like this, just think about both type 1, type 2 errors. Imagine you're in the C-suite of some industrial complex in Canada, maybe a CEO. And I would say for this one, type 1 error is more concerning because the study concludes recall it's averages we're thinking about. There's a mu up there. So we're going to conclude that the average acidity of rainfall is less than 5. In pH when the null hypothesis is true, when it is actually at a pH of 5. Then why is this so concerning? This can cause legal changes in Canada that are, I'm going to say, not necessary. Not necessary in the sense that they never found evidence that they are emitting a ton of sulfur dioxide, being less than 5. It was really right at 5 itself. So that's what's going on with the type 1 error. And again, the industry is really going to be watching how this study goes. They're going to probably be very critical on the alpha level. Even if the statistics went flawlessly, we found that the probability of a type 1 error is 5%. So if they base legal action on just one study, plenty of lawyers are going to come out of the woodwork and say, that's not fair. There's a 1 in 20 chance that the study is wrong, that's a type 1 error, and you're harming an entire industry with a pretty high chance. Well, the government can commission more and more studies. You can combine p-values and in a meta-analysis, get enormous evidence, even if all the alpha levels are at 0.05. But at one study, that's a pretty high amount, pretty high chance for a type 1 error. Well, we're on to part D. We're going to compute the power of the test. But any questions or comments at the moment? Okay, so part D says, in planning your study, recall this problem, there's no sample. We're trying to plan everything and determine what's the appropriate sample size we should select. You want to use a test that will almost always reject the null hypothesis when the true mean pH is 4.7. That's the specific alternative that we stated right here in orange, as well as up here, the specific alternative, mu is 4.7. So we want to have a test that's highly likely to reject the null hypothesis when in fact the true mean is 4.7. So it says, in other words, what is the small sample size required so that the power of the test, we're going for approximately 95%. Again, that's kind of a low amount. We could have targeted power at 99%, but we'll shoot for a 95% there. Maybe before we do that, let's say exactly what the power of the test would be in this context. Then we'll calculate it. So here's what we said power was from the screenshot that we put above. If we're thinking about the power of the test, we also want to take a look into what are the hypotheses and what is the parameter itself. So let me screenshot right here. Okay, with those two screenshots armed, let's compute the power of the test. I think we can do better on this one. If we can say in words what the power is of a test, that's actually going to help us a lot in just seeing what the computation actually looks like, how to compute it in the very first place. So let's write this out by saying power. It's a probability, much like alpha, probability of type 1 error, beta, probability of type 2 error. So power is a probability of concluding. I had a two-tailed test here, but in our problem, it's a left-tailed test. So we'll go with this direction. I'll say probability of concluding, and then read out mu less than 5, but make the substitution, say exactly what mu is, concluding the true mean. Red dot wasn't supposed to go that far up. Concluding the true mean, seems to be bouncy today. Let me try again. True mean rainfall in a Canadian forest, whichever forest that happened to be, is less than 5 in pH. All of our probabilities, type 1 error, type 2 error, and power are conditional probabilities. So we jump to this part, when in fact, the specific alternative is true. So read in, when in fact, instead of saying what the specific alternative is, we'll just write this in. So that's our specific alternative now, where the red dot is. We'll say the true mean rainfall is actually 4.7 in pH, in acidity. So that means making the correct decision is what power is, but you need a specific alternative to actually get that probability on paper. So it's a probability of making the correct decision when in fact the truth of the population is the true mean is 4.7, definitely less than 5. And that was the effect size. We had said differences smaller than a 0.3 are too negligible to be of any concern. So we want our test to have high probability of making the right correct decision when this is the actual truth of the population. It's at a pH of 4.7, so highly acidic rain. Now we're going to calculate it, but any questions first, folks? Just writing out what power is. Okay, this is how we're going to calculate it next. So let's get rid of the distracting tables. We've got power down. Now, because we're going to consider doing a hypothesis test, recall what we said in chapter 14. The very first step of any hypothesis test is you assume the null hypothesis itself is actually true. I kind of regret getting rid of one of those screenshots. Let's keep the null hypothesis here for a quick reference. So we start in the computation of power by assuming that's true. And this is where the author's decision of always putting equality in a null hypothesis, rather, even when it's a left-tailed test, starts to make sense, because that's where p-values are computed from, the direct equality, and that's where power is going to be computed from, right at 5. So we're going to say, assume h naught, mu equals 5, is true. So even if you have less than here and you wrote greater than or equals to 5 here, you would still make that assumption. Right at 5, we're assuming mu is true. So that's our number one first step in any hypothesis test. But notice the one moment you make that assumption, the central limit theorem is in effect. By the central limit theorem, the sample mean, once we get our data, we'll calculate that thing, and we'll know, under the assumption of the null hypothesis being true, it's distributed normally at mu equals 5, and usually we haven't wrote it down that way. I'm just going to write it the way we usually write it. I'll put 5 here for mu, and the sigma value was, I'm forgetting, there it is by the red dot, 0.5. So we make that assumption right away when we're going to compute the hypothesis test or conduct the entire hypothesis test. But if we're about to calculate power, we have another assumption. Power is going to be the probability of concluding the true mean rainfall is less than 5, rejecting that null, when there is another assumption in the background. So if we want power, we assume something different. Power means assume this. It's not your entire alternative hypothesis. It's a specific alternative hypothesis that mu is actually 4.7 in pH. So now there's two competing assumptions. It's kind of interesting. The overall assumption, because you're about to conduct a hypothesis test. But if you're calculating the power of a test, you put that assumption on the table at the same exact time. So we can write down this syntax for this entire test pretty fast, but it's weird looking syntax in all honesty. Or go here in the notes is to make sense of it. Why does the syntax look the way it does? How are we getting these values out in actuality? So what I'm going to draw here is one big diagram that explains how we're going to compute in RStudio and get power. So it's one overall large number line, and we're going to put down this assumption. If the null hypothesis is true, we have a normal distribution that goes about like this. It's going to be centered right at 5. So that's where it came from, that assumption there. And we're going to get a p-value when we calculate our test statistic. The test statistic is a value that lies somewhere along the horizontal axis. But the level of significance is part of this equation here. We have a 5% level of significance and a left tail test. That means there's going to be a number here. I'll just denote it as, let's call it just an ordinary z. Shading to the left of that z is the significance level, alpha, right there. So when we calculate a test statistic, if we fall in this range, below whatever that critical cutoff value is, we'll reject the null hypothesis. Now we return to the power side of this. We're making the big assumption. We're going to assume that that alternative is also true, that mu is 4.7, but then central limit theorem comes up again by the central limit theorem. Under that assumption, x bar is distributed normally with true mean 4.7, standard deviation 0.5. We'll have the same exact shape as this curve because the standard deviations are the same shape parameter, but it's been shifted to the left by 4.7. And that might be a far distance depending on how big the sample size is. In this picture, I'm just going to draw it generically for maybe not the biggest sample size. I'm trying my best to make it look exactly like the prior curve. That's kind of challenging, so we'll use our imagination a little bit on this one as well. Here's what it would look like. We're at 4.7, and that curve came from here by the red dot. Now we're ready to put on paper exactly what power looks like. So recall, we said if we are right here somewhere in this region, we rejected the null hypothesis. But if we assume the true mean is really 4.7, this is where power goes. Trying to come up with a good color for power. Let's go with this one. Power is all of this area under the curve up to the border right where z is. So it stops right there. It invades the region where we shaded for alpha. It's kind of hard to really shade that perfectly. I'll just kind of exaggerate my shading there. All of this is power. So that's what this looks like all together. We got this new probability curve because when we calculate power, we make a new condition. The true mean is actually 4.7. Then our test statistic has a high probability of being in this region to the left of the critical cutoff, which we just called a generic z. So this looks like a pretty decently high power. We're trying to get it up to 95%. Okay, again, this is pretty complicated because hypotheses tests are complicated as well. But if you talk about type 1 error, type 2 error, and power, there are 2 probability models on the table for us to consider at the same exact time. So lots going on. Any questions at all, folks, before we now delve into what the syntax looks like? Okay, well, thanks for your patience getting through this. I know it's pretty tough, but if you're doing this in the homework, the notes, the recorded lecture will be a big assist. If any questions come up, don't hesitate to ask. I'll be very happy to help out. So if we want to calculate this area under the curve centered at 4.7, you first have to find that value z. Z is going to be a Q norm because we have a probability, it's alpha. We're looking for a value on the x-axis. So it'll be Q norm. We plug in whatever alpha happens to be. It's a 0.05 in our problem. Then what we plug in next is taking a look at what z is relative to. It's relative to this curve, which is constructed from the null hypothesis. So we plug inside here mu naught. That's our mu naught in that spot. We plug in sigma, That's sigma that goes into that location. And, we're in good shape on this one because we have area going to the left, so we don't have to put in lower dot tail equals false at all in this one. We need to find that exact z value, Q norm does it, because that's the cutoff on power right here. Power is under this curve, but it stops right at that barrier z, which is informed by what is your significance level alpha in the problem. And I probably shouldn't have got rid of that. Sorry, let me scroll back and put this back on paper. Okay, just in case we need to refer to that again. Okay, now with that down, here's what power is going to be. Power is going to be equal to this area. Because it's area this time, we're going to say it's a P norm. And we want the area to the left of Z. So we plug in whatever Z is. We calculated it here. Just throw in Z. Or you could have put in the whole Q norm statement right here and just write it in as one line if you like compositions like that. I think breaking it up is just a little bit cleaner to put down on paper. So you plug in P norm at Z. Then you want the area under this curve, but that means you go over here. You have to use these values because we're making an assumption that that specific alternative is true. So you would use the mu A value. That's mu A. And this is the same sigma value. So sigma doesn't change on these. So sigma goes here, we cap it off, and that's going to calculate the power of the test for us. So we've got the syntax ready to go. All we need to do is throw this into RStudio and implement it. It's a lot of work, but at its heart, this part right here, this is just chapter 11 stuff that we practiced using the normal distribution. So here's what it looks like finally being thrown into RStudio. Notice the different values we have to work with. We need to say exactly what is the significance level alpha, the mu naught, the hypothesized value, and the mu A coming from the specific alternative. But the question here says, in planning your study, you want a test that will almost always reject the null when that specific alternative is true. What is the small sample size required so that the power of the test is 95%? Really, the fundamental thing we want is the sample size. So let's throw in some value. N equals, let's go low and start with a 4. Probably isn't right, but we're going to increase the sample size as we run the syntax until we hit 95% or just exceed it. So that would be the first thing you want. Next, let's plug in the hypothesized value. In our original null and alternative, we write that as mu0 for mu naught. It's a 5 in this problem. Sigma is a good value to put in next. So let's say sigma is 0.5. We absolutely want this value, the specific alternative value, 4.7. We call that mu A for specific alternative. And I think we have just about everything. Oh, one last thing. Don't forget, you also absolutely need your significance level alpha. That's how you get the cutoff Z right here. You had to use the fact alpha is at 5% in this problem. So alpha gets 0.05. So these are the values. If you decide to reuse this syntax, you'd want to definitely change these first. Okay, so after changing the values to match whichever problem you're working on, next thing to do is throw in this Z value. Z gets Q norm, alpha, mu naught, sigma. Then last line's power, I wanted to output power, so I'm just going to say this. Power of the left tailed test will be P norm, Z, mu A, sigma. So all we've done is just write in what we put on paper right inside the syntax. Now we're ready to calculate power for the very first time. It's kind of exciting, but any questions at all, folks? Seeing how the diagrams work informs the syntax or implementing it down here. Okay, So let's go back to the original question. We want the power of the test to be 95%. Again, that's a weird choice. This is a high stakes problem. 99% makes more sense, but the conflict here is that statistical studies, high samples are expensive. The Canadian government might have a limited budget, so this is what they asked us to do. Go for 95%. If we say the sample size is 4, here's the power of the test. 15% if we round, 15% chance of correctly rejecting the null hypothesis when that specific alternative is true. That's really bad. And industry is probably going to calculate their own power computation once you publish the study. If they can report to the media the power of this test was only 15%, again, the whole study starts to collapse, much like how they are going to complain alpha is at 5%. So we bump up the sample size. Here's what we don't want to do, though. Surely we could take, what's that? 4 million rainfall samples. That's possibly unfeasible because this is rainfall on different days in Canada. Well, if we went for something extreme, no change, looks like I made one big critical flaw. Oh man, and I made it in a couple spots. No change because the syntax and central limit theorem is wrong on this. Let's revise as we go. I got the same probability. It's as if the sample size didn't do anything. But here's the mistake. Let me fix these in 1, 2, 3, 4 spots. That's a kind of an awful mistake. But it's kind of a good mistake just to remind us, we're talking about the central limit theorem. This is one aspect that's crucial here. It incorporates the sample size. So if you saw this and you were just like, oh no, this isn't going to work out, good on you. It has to be divided by the square root of the sample size here, divide by the square root of the sample size here, and then finally, down here, divide by square root of sample size n, and one last one, divide by square root of sample size n right here, and finally, that's the correct application of the central limit theorem. That's the most important theorem in statistics, so that's a crazy blunder, but now we know what not to do, so don't make that mistake. Does that make sense to folks on the fix, the parts in red? Okay, we fixed it on paper, so let's fix it on syntax. Divide by the square root of the sample size n. Here's what it would look like here. And in this one, sigma divide by the square root of sample size n. I think I have a delimiter problem on that one. Let's close that last parenthesis. Okay, so let's go back to sample size 4 and see how this changes. It's not 14%, roughly 15%. If we take 4 samples, it was really 33%. Still not great, right? 33% chance of making the right conclusion when this is true is still abysmal. And again, the conflict here is we put in something like 400, maybe 4 million, but again, that's kind of infeasible in the context. If we say we want to study with 400 rain samples, and that's a lot, power of the test isn't 100%, but the system had to round up to 1. But this isn't the right answer either to the problem. When we're trying to target 95% for power, what we really want is the smallest possible sample size that gets us just above 95%. So if we were at 4 for 30%, maybe we'd go to sample size 10. That gets us to 60%. Maybe go big and go to sample size 60. That takes us to 99%, and that's great. But when we do this as a homework exercise, again, we can't say sample size 60. It gets us past 95%, but the government wants us to work as cheaply as possible. Or if this was a study commissioned by some other organization, maybe a company, they want to save money on this. They want high power at a low cost at the same time. So we have to change this up, maybe try, how about 40? 40 is still really high power. We're trying to get to 95 so we can make it even cheaper. How about 30? 30 is, almost there. That rounds to 95%. But what we really should do is we should get above 95%. We're not trying to hit it exactly. We want the small sample that just barely crawls above that goal, 95% power. Let's try 31. At 31, we've exceeded, but that's the smallest sample size that will exceed the 95%. So this would be the answer to our question. A sample size of 31 gives the power at 95.5%. So we'll come down here. Everything was just to organize the problem, and we can say for a conclusion, a sample size n equals 31 gives power equal to 95 point, and I forgot the rest, let me double check, 95.5%. So we did it, folks. This is computing the power of a test, finding the smallest possible sample size that will get us to the right power. I want to put a box here just to convey that's the answer to the question, and much of the work above is just the discussion for the sake of the lecture notes on how we got there. Again, when you run this, don't forget square root of n's, dividing sigma by that value. That's a pretty serious blunder. You're not using the central limit theorem unless you do that division right there, modifying the standard deviation. Any questions at all, folks? Getting through all these computations so far? Okay, this is the major meat of the notes, but I want to just take some time to reflect on what have we done here versus what we've done with confidence intervals. For power of a test, we're trying to have high probability of rejecting a null hypothesis like that, given that some specific alternative like this one is actually true. But when we were doing confidence intervals, it was quite a bit different. All we wanted to do was target one specific margin of error. We need to say what the sample size was to get that margin of error to the right specification. And we did the same kind of thing in practice. We stopped at 182 runners because we were rounding up to the nearest integer. But surely we could have said 2,000 runners, and now our margin of error is smaller. But this is pretty similar to an effect size. We want to find a sample size that's as small as possible that gets us to the right margin of error. And we just happen to round up in this situation. So it's really the same sort of problem, but when you turn it over to hypothesis testing, a whole bunch of stuff extra has to happen, and the computations do get messy. The good news is we'll share the syntax when we're doing this as a homework problem. The hard thing in the notes will be saying what power is, what type 1 error is, what type 2 error is. But doing the power computation, really it's as fast as this syntax right here indicates. So let's share that. The last thing we're going to do is just look into a couple concept questions relating to power. And then with the remaining time that we have today, we're going to turn over to chapter 17. Well, any last questions, thoughts, or comments at the moment, folks? Okay, here's what the concept questions look like. They're actually not too bad in a certain sense. I think you'll like them. I think the confidence interval confidence questions in chapter 14 were trickier. Part E says, and then again, we can't necessarily do this. Once we decide on a significance level alpha, we cannot change it. But if we're still in the planning side of the study, we can assess these kind of questions before we've collected any data at all. We're being asked, if the significance level alpha decreases, will the power of the test go up or will it go down? And there's two good ways to answer this question. One way is just look at the diagram. And another good way is, well, alpha is right here in the syntax, just decreasing the syntax, see what happens. Let's first think geometrically. If alpha decreases, Well, that means this area right here is getting smaller and smaller and smaller when alpha gets smaller. And that means the z, it has to move to the left more and more. This is at 5%. If alpha is at just 1%, z moves way over here to the left. But z is also a boundary where power ends. So if z moves to the left, power actually goes down. Decrease alpha, power will go down. And that's kind of nice because that means these change in the same direction. Seeing is believing, so we looked at it geometrically, but some people think better in these terms. What is the syntax going to do? So I ran this once already, got 95% power at sample size 31. But let's suppose we were really wanting strong protection against a type 1 error, and the study is designed at alpha is at 0.1. We just decreased it by a lot then, right? So alpha at 0.1, power has dropped down, not by a ton, but enough to make a difference. It's only at 84.5% now. So that's power going down when we decrease the significance level alpha. Let's put it back to where it was. So that's one concept question down. And this is kind of nice. They change in the same direction. Likewise, the other part of this was the effect size. How does the effect size enter the picture? Well, the effect size was telling us the smallest size of pH that was practical to us. If we instead wanted to say, actually, the pH of small size that's of practical importance to us is 0.1 in pH, not 0.3, an effect size of 0.1 would have made this a 4.9. That means this entire curve drags over to the right until we're somewhere around here. Z doesn't move at all. That barrier stays fixed. And so power, if its whole curve moves to the right, it slams against this barrier, and we're subtracting off a ton of power this time. So my claim is, if we decrease the effect size, power will go down. Thinking geometrically again, smaller effect size means we're subtracting, say, 0.1 from the original mean of 5. So this is a 4.9. Moves this to the right. Well, let's see what the syntax will do. We're back to 95.5% power. And smaller effect size means we're testing a specific alternative of 4.9 as an example. This time, power comes out way, way lower. This is a humongous change versus, say, alpha being at 5%, going to 1%. It didn't do this. This is power being deleted by quite a bit, just 30% power now. That's because if we make the effect size smaller, we're demanding a lot of extra precision in confidence intervals and in the hypothesis test. And we're being absolutely punished for that. We need to bump up the sample size a lot now to get back to 95%. So power goes down as the effect size goes down. Notice the pattern. This is kind of helpful for our brains. These both change in the same direction. Decrease one, you decrease the other. So that'd be wonderful if that pattern continues on. And you know what? It does. That's the kind of miraculous thing about power. It's not as hard to determine what's going to happen, like, say, concept questions with confidence intervals. Those are trickier. Things happen in different directionalities. But this one seems just more reasonable. If the sample size decreases, power should go down, right? There's no way power goes up if you take a smaller and smaller sample. That would be demanding take sample size 1 for the most power possible. So sample size decreasing must absolutely mean, if there's any logic whatsoever in statistics, power goes down. This one's a little bit tougher to visualize. If the sample size gets smaller, here's what happens. Sigma changes. It gets bigger. That's because we're dividing by something that's going to get smaller and smaller and smaller as the sample size gets smaller. then the whole overall value of sigma is going to get bigger and bigger. And when that gets bigger, what happens to these is they widen out a whole bunch. If they widen out, then this Z barrier is going to change, and a lot of the power is going to be pushed to the right, stopping right at the Z barrier. Power definitely goes down if we decrease sample size. It's really hard to visualize, but we can see it here. Let's go back to original effect size of 0.3, so 4.7. We're at 95% power, but then we decide to take sample at size 3. Power is dropping a humongous amount. It's now below 30%. So these are really nice power changes in the same direction as both the significance level alpha, the effect size, and the sample size. I'll leave this diagram here just for reference. Once again, thinking about power. Any questions whatsoever, folks, on any of the concept questions? Okay, we've pretty much gone through power. This is the whole problem. But I have one extra additional exercise, and this is mostly for the homework. We did power in a left tail test situation. I'm not going to ask you to do one in a two-tail test, but if you're curious, I have syntax here that's ready to go. But if it's a right tail test, and I think the homework is right tail test, unless I'm misremembering it, just in case it is, we need to adapt our syntax, and this is what it would look like. How should the syntax be adjusted? In the right tail test, we'll go change these first. This is power for now right tail test. But I think you'll like the change. It's nothing major. We just put in lower.tail equals false here. And lower.tail equals false here. And that does it. The syntax is now ready to go for any right tail test that could come up. You definitely have to change all the values that you have to get from the context of the problem. Run this syntax here, and you'll get power, just like on the prior problem with the left tail test. Well, that was the last one for the notes, folks. Any questions at all getting through chapter 15? Okay, with this out of the way, this is where our class named Statistical Methods really starts to get going. Essentially, everything we've been doing was kind of get everyone on the same page type material, because this course has no assumptions whatsoever of a statistics class prerequisite. We had to talk carefully about what a confidence interval is, a hypothesis test, matters that we just got through in chapter 15. But if you have real world data from a random sample, hopefully a simple random sample, we aren't actually using the chapter 14 method. That was just us learning what a confidence interval and a hypothesis test is in the first place. We're most likely going to be using, say, a chapter 17 method. Or if there's more than one quantitative variable, quantitative with categorical variables, we'll look into a whole slew of methods, building out a toolkit to match the statistical problem with the remaining time we have in the course. We're getting through it almost into midterms week. So here's how chapter 17 starts out. We're really just revisiting what a confidence interval is and what a hypothesis test is from scratch once again. But we've been complaining a lot. Well, I've been complaining a lot. When we were in chapter 14, we made some pretty heavy duty assumptions that weren't fully realistic. For example, we assumed that we knew the population standard deviation sigma, even though the population mean mu was an unknown. When we assumed we knew sigma, it allowed us to calculate this z-test statistic right here. We state a null hypothesis and we assume it's true, so we know the value mu naught. We collect data and we calculate x bar, so we know the value of x bar, and we'll certainly know the sample size. But we assumed also we know the population's standard deviation sigma. There's rare situations where that can happen, but in all honesty, it's not a very applicable method whatsoever. So, revisiting, it says, we gather a simple random sample of size n for a population with a mean mu, standard deviation sigma, we have the central limit theorem that tells us the sample mean is distributed this way. We make an assumption that the null hypothesis is true, but if we subtract off the mean, divide by the standard deviation z, we've standardized this variable, going from that normal to the standard normal curve, n0, 1. Subtract off the hypothesized mean, the mean is now 0. Divide by the original standard deviation, and the new standard deviation is 1. So our test statistic followed that standard normal curve. We call these all z procedures, but here is the reality of just about any real-world set of data. Both parameters are actually unknown. You may still have a null hypothesis, so you'll assume the null is true and know mu naught, but you won't know sigma. That's a total unknown. We can still come up with an estimated value for the test statistic z, and this is what people were doing in practice about 100 years ago, until people like Gossett and Fisher got together, wrote a bunch of letters. Gossett found out that there's a problem here and came up with a new test statistic that resolved it, with a new distribution called the t distribution, published under pseudonym Student's t distribution. So let's go through what had to be done. We still need to do a test, so we're going to estimate the test statistic z, which means you have to estimate sigma. And that's okay. X bar is already an estimate of the population mean. So why not use the sample standard deviation S to estimate the population standard deviation S? It's absolutely logical and it's the right step to take. So we'll say here, first, estimate sigma. It'll be approximately equal to S, which is the sample's standard deviation. So that'll be our first step. Then that entire denominator, which came from here in the central limit theorem, we can just estimate the whole thing. Sigma divided by the square root of n will be approximately equal to S divided by the square root of n. And again, that's important because S is a known value, just like the sample mean is a known value. Once you have the data, you have both the mean of the sample and S, the standard deviation of the sample. We can actually calculate that now. It's an approximation, so we need to be wary. And here is our estimate. Then Z can be estimated by, we give it a new name, T, for a T distribution. T is going to be X bar minus mu naught. Both values in the numerator are now known. Mu naught comes from the null hypothesis. Then we divide by S, which is divided by the square root of the sample size n. And we certainly will know the sample size, so this is something we can calculate. It is directly an estimate of Z, however, and so we have a curious kind of problem. But any questions at all, folks? Just getting to this stage here. Okay, well, people just went with this historically. Over 100 years ago, they calculated back in the normal distribution. Once again, they just reused the standard normal curve. They got their p-values, they got their confidence intervals, and then they moved on with life. But Gossett, who came up with the t-distribution, was working with very small samples. He was dealing with breweries, dealing with batches of beer, and these are large experiments that take a lot of time. His sample sizes were in the 3s or the 4s. And he noticed that this estimate is very dangerous when you have small sample sizes. It's even problematic at large sample sizes, but he was able to detect something is wrong. The logic's breaking somewhere when he used the normal curve in his experiments. Here's where it's breaking. Let's go all the way back to our major complaint about the course. We can write down what the parameter mu is and what the parameter sigma is. That's the population's mean That's the population standard deviation for sigma. And we can absolutely estimate them. We collect the data, we crank out the statistics. The mean of the sample is X bar. The standard deviation of the sample is S. And then we make a point estimate right here. The unknown mu is approximately equal to X bar. But there's a major complaint with that, right? The reason we've been doing all of these statistics is because that estimate is absolutely worthless until you specify the margin of error. And notice that applies to sigma too. Sigma is not special either. There is a margin of error in making that estimate. If we don't say what it is or incorporate it somehow, we are not doing statistics correctly. This is a mistake unless the margin of error in making that estimate is brought into the picture. So when you use the normal distribution, we are not saying we had any error there. We're treating this as an actual equality. But we're going to skip over to a t distribution, as a lowercase t demonstrates or hints at. That does include the error in making that estimate in the very first place. The error is larger at smaller samples, but it gets minimal at larger and larger samples. So first, next part of the notes is just formalizing what we've done so far. That s divided by root n is so special, we'll call it the standard error of X bar. So whenever you see SE, think of that as just shorthand for standard error. Error not in the sense that we made a mistake, error in the sense that there is a margin of error there that we have to incorporate into our method, or else our statistics will have a massive logical flaw that we're not willing to accept whatsoever. And it's written in function notation because we're going to put other things in there. It could be standard error of p hat, the sample's proportion, or it could be the standard error of X bar 1 minus X bar 2, the mean from two independent samples, and so on. So we'll often be just referring to SE for standard error. We take the sample standard deviation, divide by the square root of n. We get that approximation like we mentioned above in the notes. And the standard error is the exact standard deviation of X bar, approximates, the exact standard deviation of X bar, which is at sigma over root n. Approximation does improve as the sample size gets larger and larger, but what we'll do next is incorporate the error by ditching the normal N01 distribution and going to the t distribution. So that's the story so far, and the logic of why we're suddenly not using the normal distribution. What we'll turn to next is the t distribution itself. But any questions at the moment, folks, with the t-test statistic so far, or the standard error? Okay, so I put this down just to have a place to say, if we can write down a mathematical function from the normal distribution, we should be able to write down a mathematical function for the t distribution, and that's what this is down below. We're not going to calculate it with it as it stands. This is more for the sake of the curious. It's a pretty convoluted, massive function that relies on a gamma function, which is itself an improper integral, integrating from 0 to infinity, of a pretty complicated looking function. But here's the story so far. It says, we draw a simple random sample of sample size n for a population that has a normal distribution with mean mu, standard deviation sigma. We can in fact delete this with our robustness conditions later and rely on central limit theorem. But for the moment, we'll let that assumption stand. The one sample t-test statistic looks like this, the same one we did before, but the standard error incorporated inside of it. So we take the mean of the sample, subtract off the hypothesized mean. Oh, I noticed that there's an error there. That should have said for hypothesized mean. Sorry for the distraction on that. That should be a mu naught. Let's highlight that in red. That's a definite logical error without a 0 there. Because in practice, that always comes from the null hypothesis. Sorry for the distraction on that one. I just noticed that typo. So once we calculate that t test statistic, again, we've made an estimate, the standard error. The estimate is going to be encapsulated inside the t distribution. You'll depend on the degrees of freedom, which is the sample size -1. And it's an ugly function, but let's still plot it just for the sake of taking a look at what it even is. What does the t distribution look like, and how it depends on the degrees of freedom n -1. The core thing we're doing is taking the fact that SE, standard error, of x bar is approximately equal to sigma over root n, and the t distribution incorporates the error, the margin of error in making that estimate right there. So again, this is a kind of scary part of the notes, but this is just mainly for the curious of what is the function for the t distribution. Here it is, a pretty hard function to compute with. So you can imagine 100 years ago when people were first using this, they had to work really, really hard on coming up with just a single value for the t distribution. It took them years to build out a table, for example, and they had to use tricky methods to estimate these kind of integrals. But we have some fancy technology, and the purpose of this syntax is to plot both a normal curve and the t distribution at once. This syntax took a lot of time to put down on paper, so we'll focus less on what the syntax is. I have it in the notes for the curious, and focus more on the graph that's going to read out to the right. So my red is going to be the t distribution, blue is going to be the normal distribution. My degrees of freedom is set to 4, which means the sample size is 5. And this is what the picture looks like. We have a normal curve in blue. That's this blue line going through here. We have a t distribution in the red line going through right here. And if we were doing, say, a 95% confidence interval, here's what the picture would look like. In a 95% confidence interval, you're trying to capture the central 95% of the standard normal distribution. And in doing that, you would have a critical value here, z star. We know that's about 1.96, and a negative z star here. So that's your critical value for z star and using the normal distribution. But if we omit, we don't know the population standard deviation sigma, and we make this estimate, sigma over root n is approximately equal to s over root n. It's the same problem we've been complaining about from day one. We have to capture the error in that estimate, and if we don't, the estimate is completely useless. The t distribution at 4 degrees of freedom does capture that error. So this is an ingenious distribution curve. In making that estimate, you get a critical value t star, which is clear over here. Red is the shading under the t distribution. It's very heavy-tailed at a sample size of 5, giving us degrees of freedom 4. So if we're sampling at sample size 5, and we want a 95% confidence interval, our t critical number is not 1.96. This is what Gossett noticed right away. His experiments were not panning out at all. The critical number is probably like 2.75. So that's the picture so far. And this is kind of a terrible picture at a low sample size of 5. Any questions at the moment with the curve at sample size 5? Okay, there's an improvement here though. If we bump up the sample size, if degrees of freedom it goes from 4 to, say, 15, that means the sample size n is 16. Degrees of freedom are 1 less. Notice what starts to happen with the red curve against the green curve. The error in making this estimate is not as big if you go to a larger sample size. The error being not as big does this. The area under the t distribution, 95% of the central area, gives you a t critical number now right here. It's still bigger than z star by a good amount. It's something like 2.3 approximately. We'll show how to compute it exactly. So even at a sample size of 16, the error here is substantial. and it's captured right away. Now, when we use our test statistic with a standard error or do a confidence interval with the T star we see here, we are really doing 95% confidence, or we're really capturing something at the right power. The story gets even better, so let me erase one more thing. Even if the curve is original population isn't normally distributed, if our sample size goes around 30, the sample statistic X bar is distributed normally, and the T distribution is still relevant. So at sample size 30, here's what happens next. Notice that the red curve, the T distribution, and the blue curve are about the same, and the T critical is right where the red dot is. It gets closer and closer to Z star, the larger and larger your sample is. We go for something like a really large sample, say sampling at size 200. This will give you the central limit theorem being effective in most situations. You have to work hard to find a population where central limit theorem still doesn't work at that large of a sample. And what will happen with the areas? We can't quite see it here, but T star and Z star are very, very close, yet T star is still bigger. We should still use the T methods because we want our intervals and our hypothesis test to go as honestly as possible. There's still an error in making this measurement at any sample size. So even though they look close, the area for the T distribution is slightly bigger. So that's what the curves look like. Let me bring this down to something more dramatic, say degrees of freedom 9 for a sample size of 10. You get this picture here, and so T star is here. T star is absolutely larger than Z star at any sample, but here at sample size 10 for degrees of freedom 9, it's noticeably larger just on this geometric object, looking at the graphs. So that's T scores versus Z scores. Let's put this down below. We now need to know how to calculate our T star values, our T criticals. But once we do that, the good news is, check out how nice our confidence intervals are. We'll definitely discuss robustness conditions. We'll come back to that, but our confidence intervals looks almost identical to what we did in chapter 14. We start with the point estimate, X bar. We put in a critical number, it's T star this time, so we'll show how to compute that. We multiply by a standard error, that's S over root n instead of sigma over root n. So we're never going to state a sigma value any longer. We're going to just admit fully and honestly, we don't know. If we don't know the parameter mean mu, and we're estimating it, we almost assuredly don't know sigma either. And so this is going to be our first bona fide statistical procedure that works in very, very wide applicable applications. Well, we have a lot to talk about still. We want to talk about the conditions, the honest conditions for using the hypothesis test or confidence interval. Then we'll run through several examples, just like we did in chapter 14. It's a great opportunity to just relearn how the intervals go, how the hypothesis tests go, before we turn into bigger problems. Well, any last questions at all, folks, before we call it a day today? Okay, and again, congratulations for getting to this part of the course. Chapters 13 and 15 in particular are tough, but once you take a look at chapter 14, 17, 18, 19, 20, I think this is where the intensity kind of tones down. We're going to be stating confidence intervals, computing them, interpreting them, just like we did in chapter 14, and same with the hypothesis tests. But have a great weekend, folks. We'll be back to this part of the notes next Monday.